Hey everyone, so now that we have a good idea about all the constraints, at least roughly, let's have a look at the first one, and that is just pinning stuff in space. So what we have here is a very simple basic setup, nothing special, nothing complicated, just a planar patch falling on top of a collision geometry. And it's actually quite simple to now pin some of the points, maybe all four corners, let's say, into space, because that's already built in the main constraint here. And it's right in the middle. It's called pin to animation, and it says pin to animation, and we will actually look at this in the next video, but this is the same function that we can use to simply pin something in space. Now by default it's actually quite simple. You have a little arrow here, you can click on it, and then you can just select on your active simulated geometry what kind of points you want to pin in space. I press enter, and if I press start, it's actually pinned. So very easy. End of video, right? Well, not quite, because what I just showed you is something you should usually not do, because it's, as we've learned from the one of the very first videos, a very un-Houdini way of doing things. Whenever we see point numbers somewhere, we should be careful, because now it's not procedural anymore. Because what happens if our input geometry is changing or we add additional geometry to it, then this will break. I mean, you can do this, you know, if you need something quick and dirty, that's totally fine, but let's do it a bit more elegant. And since you can see this is actually a group input, let's actually use groups. Before we do this, let me show you another little thing though, and that is we can actually, instead of creating our own groups, just use groups that the planar patch can export. Because here under seams, you can actually activate, for example, left seams and right seams groups. And then when you middle click, you can see it creates a planar patch left and planar patch right, which is based on the naming here. It uses the name of the node and then left and right. And unfortunately, there is no way of showing where this is, but let's just use those groups in the pin points parameter here under pin to animation. And here you have them. And if you want, you can, use something like planar patch star or something, or maybe one and star, and then it will find every group that comes out of it. But as you can see, you can just, work like with normal groups. And keep in mind, those are point groups. This is important when we create our own groups in a second. And now when I press start, surprise, it actually works. Depending on what you want, of course, this is not all four corners. This is just, edges, but maybe that's exactly what you're looking for. And then you can save a lot of time by using the planar patch seam groups. So let's turn this off. We don't need this. What we want to do is we want to use our own group. So let's get rid of the group here. And a simple group node, of course, will do. Make sure it's a point group, and we call this pin just to be clean. And of course, you can do something like a simple bounding box. So let's say I'll move this here, and then all those points, when I choose them here in the pin to points drop down, will be pinned actually. And of course, what we can also do is we just take our own input. So let's switch this to bounding object. And since we have a point group here, this is perfect. And the advantage of this is that we can use multiple boxes, for example, to find just the corners of our geometry. Here we go. I managed to do a single one, not too shabby. And now, of course, you can just copy that box and move it somewhere else, which can be helpful if you have, some irregular points that you want to pin in space. You can then just, use one box for one pin position. I don't know, maybe something over here. And then you just merge them together. A quick way is just Alt, and then it creates a merge, and there you go. And now all these boxes will create areas where our planar patch is pinned to, and our group is still set. So as you can see now, we can now position the pin areas any way we want, and this will still work when our planar patch is changing, let's say the resolution. And if you rewind, we can see it still works even with a lower resolution. Now an alternative, by the way, would be to bit more elegant, maybe a copy and transform, and then move one box to one corner, and then do this again in the Z direction in my case. And then you don't need necessarily 4 boxes. That's another way of doing it. Then as you can see, that works pretty fine. No problem with that. Let's increase the resolution again, by the way. There you go. As you can see, a pretty flexible and still procedural way of doing this. But there's an even better way if you're a bit more familiar with Vex, and we will use something that is actually explained in the Vex chapter. We can actually procedurally find those corner points with Vex. We don't have to always, position them by hand, because when you look closely, there is a certain rule to what is actually a corner point, and that is how many neighbors it has. So for example, this point here has 1, 2, 3, 4 different points connected. There you go. Then this one here has 1, 2, 3, 4, 5, 6 connections, and anything in the corner only has 1, 2, 3. Now feel free to stop this video and count for every single point to see if this is actually a general rule. But what you will find is that only the corner points, as long as they come from a planar patch, will have only 3 neighbors. That's true down here, 1, 2, 3, and also here, 1, 2, 3, only 3 connections. So we can use this by just creating an attribute for those corners. And what we want to check for the current point that we're running over is how many neighbors it has. And for this, there's a function called neighbor count. There you go. And the input of that is first the geometry number, which is the current one, so 0, and then the point number that we want to check, which of course is the current one, which we can read out with ptnum. And if what comes out of this function is 3, then we know we have a corner. Usually the way I do this is not checking for exactly 3, but I do something like smaller than 4, because then I know it will definitely be a corner. And when this is true, then let's create our own little attribute, and let's call it corner, for example, but it doesn't really matter, and set this to 1. So if we quickly check what comes out of this for our points here, we have a new corner attribute, and if we sort it, we can see only for 4 points this became 1, so it seems like it worked. So let's give that a try. And how can we use this? We don't have a group anymore, so we can get rid of this. But as you know, instead of using a group, we can just check for certain attributes. So we can check, for example, for all the points where the corner attribute equals 1. Technically, it should look like this, but as we know, the Vex expression is a bit strange, so it actually works like this as well. So let's try if that worked. And as you can see, yep, that actually worked completely via Vex. So let's call this maybe find corners or something. And this, I use quite a lot because it's a pretty elegant way of doing this. And of course, it's also fully procedural, because as soon as my geometry change, this will adapt to it. It's not a must, if you don't feel comfortable with Vex, that's totally fine. Just create your own groups. No problem with that. But I just wanted to show you a little trick where we can use the neighbor count function, because for this, it's perfect. Okay, so this was pretty straightforward, just to hang any point in space in a Vellum simulation. Many different ways we found how to do this. In the next video, we want to have a look at how we can actually animate those points, or take an animation that is on those points and follow it. So I hope this is helpful for now. Thanks very much, and see you later. Cheers.